Chapter 4, bonus multiple choice video. Hopefully some of you are watching these and getting the experience needed to do better on the multiple choice, on the exams, and for the AP exam. So again, I take an old test and take its multiple choice so that it should be pretty similar to what you should see on the actual test. So first off, we have what electrical changes occur in muscles as they get tired. Student subjects are instructed to hold their arms above their shoulders as long as they can. Meanwhile, the electrical activity in their arm muscles is measured. This is, well, let's see. Let's go through these one at a time. An observational study. Are they just watching what's happening? No, they're actually doing some measuring here, right? Because it said the electrical activity in their arm muscles is measured. So it's not an observational study. They're not just watching and seeing what happens. They're actually measuring something. So this is some sort of experiment, right? Is it an uncontrolled experiment? Well, what would that mean exactly? It would mean that whatever data that they gather from their arm muscles, that they don't have anything to compare it to. You know, what's normal arm muscle electrical activity so that we can compare it to the students that actually hold their arms out? Well, that's pretty much what's going on here. There is no control group to compare our, did they say how many students? No, just that student subjects. So all of them did this. So they have nothing to compare it to. So this is an uncontrolled experiment. Let's just go through the others to see why they don't match up exactly. A randomized comparative experiment. Well, again, there's nothing to compare, right? That's why it was an uncontrolled experiment. A matched pairs design. Well, it would be a matched pairs if they did this, what they did up here, if they did it to all the students and then did it without having their arms above their shoulders for as long as they can. If they just measured what normal electrical activity is in their arm muscles. So it's not a matched pair. Impossible to describe unless more details of the study are provided. Well, we already confirmed that this is an uncontrolled experiment, so it's not E. So it must be, in fact, B. Number 2, which of the following statements is false? A, non-response can cause bias in surveys because non-respondents often tend to behave differently than people who respond. Well, we found that to be a true statement. Those that feel like they have strong opinions will absolutely respond, and typically the results that we get back from those surveys will either grossly overestimate or grossly underestimate the true population opinion on whatever the matter is that the survey was focusing on. So this is a true statement. B, non-sampling errors can distort the results of a census. And yeah, I mean, non-sampling errors were any type of error not related to the sampling process, which could include, mistyping data into our calculator or computer for that matter. So yeah, that can really distort the results of a census if we put in wrong numbers into a computer. Slight changes in the wording of questions can make a measurable difference in survey results. I would say that would probably be a true statement. You know, if you leave out baiting words or leave out colorful adjectives, that probably could make a measurable difference. So I think that's probably a true statement. People will sometimes answer a question differently for different interviewers. Yeah, I mean, that was a response bias where, if we were being asked questions about race and someone of a different race compared to us was asking us the question, we might respond differently than what our true, intentions might be. So I believe that would be a true statement. So that leaves us to E. Sophisticated statistical methods can always correct the results if the population you were sampling from is different from the population of interest, for example, due to undercoverage. That would definitely be a false statement. No matter what type of methods that you use, you can't overcorrect for having the wrong population of interest. That'd be like saying, well, I only asked freshmen and I really wanted the seniors' opinions. No matter what I do to my numbers, I can't overcome that difference between getting answers from freshmen and trying to apply them to seniors. So that absolutely must be the false statement there. No, you can't do anything mathematically to account for that. Number 3, an experiment to measure the effect of giving growth hormones to girls affected by Turner syndrome was carried out recently in Vancouver. All 34 girls in the study were given the growth hormone, and their heights were measured at the time the hormone was given, and again 1 year later. No measurements were made on their final adult heights. Which of the following is not a problem with this experiment? There was no blinding. Well, let's see. If there was blinding, that means someone would have to know who's not receiving, say, a treatment or giving a treatment. But really, all 34 girls were given the growth hormone. So everybody knew what they were getting. Everybody knew what they were giving out. So that's not really a problem here. B, there was no control group. Is that a problem in the experiment? Which is not a problem. So control group. Is that not a problem with this experiment? Not really. I mean, we can see their growth hormones, how that was not affecting them before it was given, and how much later, if it really did boost their heights. So I don't think that's really a problem necessarily. It'd be nice if we had a control group to compare to, but it's not a problem with the experiment necessarily. So I would say B is not necessarily a problem. Non-response bias. Well, again, here's the thing. All 34 girls were involved, and they measured the heights before and after the hormones were given. So there is no non-response bias. I mean, all of them were affected. So C is my answer there. That's not a problem, again, because everyone applied here. All 34 girls were given the treatment, and their heights were measured afterwards. So there was zero non-response bias. All right, there was insufficient attention to the placebo effect. Not necessarily a problem with that. It's maybe something to consider. Because final heights were not measured, it is impossible to tell if the hormone affected final height or only accelerated growth and made no difference to final height. Well, there were kind of two heights that could have been measured. They measured the height 1 year later, but they didn't look at their final adult heights. I think the main thing they were trying to look at was, in a 1 year period, did it accelerate their growth? So I don't think, again, that's an issue. That's a problem. Number 4. We wish to draw a sample of 5 without replacement from a population of 50 households. Suppose the households are numbered 0, 1 to 50, and suppose that the relevant line of the random number table is the following. Then the households selected are, so let's see, who would we hit? First we'd hit house 11. Boom, all good there. Then we'd hit house 36. Oh, okay, so we've knocked out A. So how did they get 13 on A? Oh, what they did was they did 2 numbers and then looked at the second and the third, and then they did the third and the fourth to get the 36. So they were reading it incorrectly. All right, who's next? 23. Can we have house 23? We can. So we've knocked out E. How did they get 96? I don't know what they do. They said skip the 2, 3, and I jumped to here and got 96? Is that what they did? Oh, yeah, they had 35 there. Oh, I didn't even mess that up. So we already knew E was wrong after the first one. Yeah, so they were just looking at the first 2 numbers, first 2 numbers, first 2 numbers, first 2 numbers. So that didn't work. Okay, now we know how they got the 96 there. Okay, so we continue on. Household 56. There can't be a household 56. It only goes up to 50. So D's knocked out. 92. There is no household 92. 96. There is no household 96. 23. That works. But 23, we already had a 23. And this said without replacement. We don't put the 23 back in. That would be with replacement. So C is taken out. So technically, if we couldn't do 23, we'd keep moving on 79, and then we could have 8. That would work. And then last but not least, we could have 42. So B is our actual answer. Number 5, a civil engineer is testing the reliability of traffic signal controllers produced by 2 different companies. He has 20 sets of controllers from each company, and he has been given clearance to install them at 40 different intersections in the city. He randomly assigns the controllers from company A to 20 intersections and the controllers from company B to the other intersections. The most important reason for this random assignment is that randomization is a good way to create 2 groups of 20 intersections that are as similar as possible so that comparisons can be made between the 2 groups. Well, that sounds pretty good. But the thing to note here, it says the most important reason, which means there's probably going to be multiple things that work, but one's going to be better than the others. So let's keep looking here. Randomization eliminates the impact of any confounding variables. That's true as well. Let's keep going on. Randomization makes the analysis easier since the data can be collected and entered into the computer in any order. Well, that's not really a good reason for randomization. Randomization ensures that the study is double-blind. Well, randomization and double-blind really have nothing to do with each other. Randomization reduces the impact of outliers. Not really. I mean, if there are outliers, they're still going to be there after we randomly, split them up into groups. So it doesn't really reduce any impact by outliers. So now we've got to look at A and B. Which one is really the better option here? Now, while B is true that it will eliminate any impact of confounding variables, the main reason why we want to randomize is to create 2 homogeneous, 2 very similar groups to each other that we can compare. So really A is the most important reason. Again, one of the side effects really of randomization is B, that it does eliminate the impact of any confounding variables. 6. To test the effects of a new fertilizer, 100 plots were divided in half. Fertilizer A is randomly applied to one half and B to the other half. This is what type of experiment or study here? Well, first let's start with observational study. Are they just watching what happens here? Well, let's see. It said we have a new fertilizer. They're going to put A on one half and B on the other. They didn't really say what we were going to be doing afterwards, right? So this kind of does sound like an observational study because they didn't say what they were going to measure. But I think we can assume that they were going to measure, growth, right, related to these 2 fertilizers. So I think they should have included some extra stuff in here about what they were going to measure. So I wouldn't necessarily say it's an observational study. We'll keep this as an answer if everything else really falls apart. A matched pairs experiment. Now, the thing to notice here is that they said each plot, and let's say this is plot 1, is divided in half. And they're going to put A somehow. We have to randomly decide which half gets A and which half gets B. Let's say B is the random for the left and A is the random for the right. Now, plot 1 might be different in some way to plot 100. And let's say A was randomly on the left and B was on the right. Now, what we're going to be able to do is to compare A with B within each plot. So there might be some difference between plot 1 and plot 100, where maybe B works better in plot 1 or within the first 10 plots, and maybe A works better towards the end of the plots. We don't really know the differences there. So there's a potential lurking variable with some confounding going on. So I would definitely say this is a matched pair experiment. Within each plot, we can compare one fertilizer to the other. So I guess we can eliminate A, that it's not just an observational study, assuming that, again, that they are measuring some sort of response variable. Completely randomized? Nope. If it was completely randomized, we would have said 50 of them get A and 50 of them get B. A block design? They didn't really say what we would block on, so it's not a block design. Impossible to classify unless more details of the study are provided. It might be more E, since we didn't really know if it was an observational study or a matched pairs experiment. So man, this one's tricky. I would still have to say a matched pairs by the way they were setting this up. If I provided a blank here and you said, I don't really know because we don't know if they're going to measure something in the end, I would give you credit for that. Um, but if this was on an AP test, that would be tough. I mean, this would be a questionable problem to put on an actual AP exam. Again, I would go for more match pair. The answer in the book was also a match pair. So I would say they're just leaving out the little bit of what they would measure in the end as a response variable. 7, an airline wants to assess customer satisfaction. Chooses a random sample of 10 of its flights during a single month and asks all of the passengers on those flights to fill out a survey. This is an example of a multi-stage stratified cluster, simple random, or convenience. Well, it's definitely not a convenience sample because they did randomly select 10 of the flights in a single month. Now, out of all of the flights that they could have in a single month, if they randomly picked 10 of them, let's say they picked that one, they randomly picked that one, and that one, et cetera, et cetera, et cetera, and then they took all of them involved, it's kind of like they're splitting them up into different groups. So stratified was kind of like splitting them up into different groups, but they would select some from each flight. But that's not what they did. So it's not a stratified. It's not just a simple random sample, because they didn't say if it was a simple random sample, then each. No, hold on. Let me get this straight here. Each subset of 10 would have the same probability of being selected. It's kind of like a simple random sample, but then this part here really doesn't make it simple anymore, that they asked all of the passengers on those flights. So it's not really simple because of that. Cluster was whenever we had groups, we selected some of the groups and then we took all of those. And that's really what's happening here with our cluster. Some of you might be asking, what's a multi-stage sample? A multi-stage sample might be maybe you split them up into clusters and then simple random select from there. You could have a stratified cluster. It's basically a multi-stage is when you're doing multiple things, and it's not just one particular thing, that it could be a combination of things. And this really isn't just a combination of things. This is just a cluster sample. All right, 8. You work for an advertising agency that is preparing a new television commercial to appeal to women. You have been asked to design an experiment to compare the effectiveness of 3 versions of the commercial. Each subject will be shown one of 3 versions and then asked her attitude toward the product. You think there might be large differences between women who are employed outside the home and those who are not. Because of these differences, you should use, well, if we think there's going to be a difference between 2 groups, we would definitely want to split up those women. Those that work, yeah, I'm doing this with a mouse, and those that do not work. And if we believe there are differences beforehand and we split them up and then ask and then carry out the experiment, essentially we are doing a block design. Stratified kind of sounds like that's what we're doing, but a stratified isn't a design. A stratified is a type of sampling method. So we can automatically really eliminate stratified and multi-stage because we're not sampling. This is really the type of experiment we should be doing here. Completely randomized, that would just be we throw all the women into one big group and then split them up and show a third version 1, a third version 2, and a third version 3. Categorical variable, I mean, that really makes absolutely no sense. So this is just a block design we'd want to incorporate. 9, according to a 1990 census, those states with an above average number of people X who fail to complete high school tend to have an above average number of infant deaths Y. In other words, there is a positive association between X and Y. So we're saying there's a association between those that fail to complete high school and dead babies. The most plausible explanation for this is X causes Y. Programs to keep teens in school will help reduce the number of infant deaths. Do we really believe that if kids stayed in school longer, that less babies would die? I don't think that's a very plausible thing that's going to happen. Y causes X, that dead babies cause teens to drop out of school. Well, I mean, that sounds like a pretty plausible reason why someone would maybe want to drop out of school. Like, well, I just had a baby and it died, and man, I can't carry on my education anymore. but would that cause 100% of those? Like programs that reduce infant deaths will ultimately reduce high school dropouts. I don't think that's really true. C, lurking variables are probably present. For example, states with large populations may have both larger number of people who don't complete high school and more infant deaths. Well, we had talked about before how even if two things are related, there's an association, doesn't necessarily mean that they're connected, that there might be other things at play like lurking variables. So this one sounds good, but I'm not necessarily going to say, boom, that's the answer, because again, this says the most plausible. So they're kind of implying that there's more than one plausible explanation. Which one's the most plausible? All right, D. Both of these variables are directly affected by the higher incidence of cancer in certain states. That may or may not be true, but I mean, I have no idea about higher incidence of cancer in certain states. So this one's, I mean, might possibly be there, but I'm definitely going to say no on this one. E, the association between X and Y is purely coincidental. Well, yeah, I think it could be just a pure coincidence, or there might be, in fact, lurking variables present. So out of these two options, which one do I think is most plausible? I would have to lean more towards C. There might be some reason why teens tend to drop out of school and there's more dead babies. Um, I definitely think there's something related there. There's something connecting those two. And it might be that those states have lower socioeconomic status. We just have a poor state. The economy's not as well off as it is. So if the economy's not very great, then kids will probably don't see the point of staying in school. If they don't see the point in staying in school, and people are poor, then they may not have as great of health coverage, and maybe more babies die because of lack of prenatal care. So I think there's maybe more of a C effect here. And the last one. 80 volunteers who currently use a certain brand of over-the-counter allergy medication have been recruited to participate in a trial of a new allergy medication. The volunteers are randomly assigned to one of two groups. One group continues to take their current medication, the other group switches to the new experimental medication. Each is asked after 2 weeks if their allergy symptoms are worse, better, or about the same as they were at the start of the study. Which of the following best describes, again, there might be more than one thing that works out here, so they're looking for the best one, a conclusion that can be drawn from this study. So we can determine whether the new drug reduces symptoms more than the old drug for anyone who suffers from allergies. Now, they're implying that this can go to the population. But again, we have volunteers here, and we said we can't apply the results of a study or an experiment to the population unless the people chosen were randomly selected. And these people were not randomly selected. So the results can only apply to the people in the study. So it can't be A. Now B is essentially saying, it's repeating the same exact thing, but it says for the subjects in the study. So we said that is true. We can conclude that. C, we can determine whether the allergy sufferer's symptoms improved more with the new drug than the old drug, but we can't establish cause and effect. Well, we can establish cause and effect. And how can we establish that? Because we had random assignment. We didn't just say, you 40 take the old stuff, you 40 take the new stuff. Since we randomly split it up between the two groups, the old and the new medication, we can establish cause and effect. So it's not C. D, we cannot draw any conclusions since that's a typo there, since all the volunteers were already taking the old drug when the experiment started. Well, that really doesn't matter. The old medication people are really providing us a control group. So we can still draw conclusions. We're comparing the new versus the old. E, we cannot draw any conclusions because there was no control group. Well, there was a control group. It was the people who were still taking the old allergy medication. So really, the true only answer that really works out here is B. Now, one question I would have is, what effect the placebo effect might have here. Because if people knew that they were taking the old medication, because they probably know what that pill looks like, and And then the people who are taking the new medication, if they really knew they were taking the new, they might feel it's a better medication and that maybe there's some sort of psychological effect, mental effect, where they believe their allergies are getting better because they're taking the new, the improved, the better pill. So they didn't really specify that this was a blind experiment, that 40 people would continue with the original old medication and 40 would get the new, but they wouldn't necessarily know which one they were getting. So that would be the only thing that would really make this experiment better, in my opinion. To make sure that it's blinded to reduce the placebo effect, essentially. All right, and that is all for our bonus multiple choice review problem session. So I hope that really helps you out whenever you get to the actual exam.